This is a recording for section 12.6, scatter plots, correlation, and regression lines. So a scatter plot is a collection of data points, one data point per person or object, right? Something like height and weight, for example, right? One person's height and weight. And we kind of expect that the taller the person is, maybe the more they might weigh. So we use the scatter plot to determine whether two quantities are related. So for correlation, a clear relationship between the two quantities. Correlation is used to determine whether there is a relationship between the two variables, and if so, the strength and the direction of that relationship. So we say that the variables are positively correlated if they tend to increase or decrease together, right? And this first example is positive correlation, right? An increase in X means an increase in Y. This one's a negative correlation. An increase in X means a decrease, right? An increase in X is this direction and a decrease in Y. And something like this has no correlation. What we're going to be specifically interested in here is linear correlation in this course. Linear correlation or linear regression, where there is a strong correlation in a straight line pattern. Example, do you think there would be a positive, negative, or no correlation between the following? Explain. Time spent studying for a test and test grade. So if we think about time spent studying, and the dependent variable would be test grade, depends on the time studying, we expect for over here little time spent studying, a lower test grade, right? But the more time spent, the higher the test grade. So we would expect it to have a positive correlation. Part B, time spent training and time to run a 100-meter dash. So time spent studying and time to run. As we can imagine, not time spent studying, time spent training. If it was time spent studying and time to run a 100-meter dash, there would be no correlation at all. But here, time spent training and time to run a 100-meter dash, we expect that the more time we spend training, the time to run the 100-meter dash should go down, right? So we expect a low time to run if we spend a lot of time training. But if we don't spend much time training, we expect a longer time to run, right? It will take us longer. So this one would actually have a negative correlation. Just because there's a strong correlation doesn't imply that there's a cause and effect relationship. Eating breakfast has long been correlated with success in school for elementary children, but breakfast doesn't necessarily cause students to be better learners. Not having breakfast correlates highly with other challenges in kids' lives, such as worse socioeconomic status, less educated parents, and lower expectation, right? So it just doesn't mean eating breakfast causes students to do poorly, or not eating breakfast causes students to do poorly in school. It's not a cause and effect relationship. There are a lot of lurking variables, right? Socioeconomic status, etc. It turns out that kids who don't eat breakfast are more likely to be absent or tardy. Breakfast may encourage kids to come to school and on time, which then improves their performance in school and so perhaps encourages attendance, which then results in better performance. So just because there's a strong correlation, it doesn't mean there's a cause and effect relationship there. A regression line is a line that best fits the data points in a scatter plot. Perfect perfect positive correlation is where all points lie precisely on the regression line. Perfect correlation means the points are exactly on a straight line. Negative perfect correlation, negative meaning negative slope, right? Go descending from left to right, which all points fall precisely on a line that has perfect negative correlation. But not all of them are going to fall in a perfect straight line pattern, but we want to know how close is it to a straight line. And what we use to measure that is the correlation coefficient, which is designated by a little lowercase r, is a measure of the that is used to describe the strength and direction of a relationship between variables whose data points lie on or near a line. So if it has perfect, if there is a perfect positive correlation in this first slide or this first graph, you can see that they fall in a perfect straight line pattern in the positive direction, then R is positive 1. Okay, so 1 is perfect, right? The correlation coefficient actually lies between 1 and negative 1. So 1 is a perfect positive correlation. 0.8 you can see is pretty close to 1 whole, right? And 0.3 is pretty low, all right? It's closer to 0 than 1. And you can see that there's not much correlation there. Correlation of 0 is absolutely no, the data values do not fall anywhere near a straight line pattern. So that's from 0 to 1. Right, so anything close to 1 over here, right, has high correlation. When you do it in the opposite direction, over here to negative 1, if the correlation's negative 1, that's actually a strong correlation as well, because it means perfect negative correlation. Okay, so that's negative 1. Negative 0.8 just means, right, the same thing as 0.8, but it goes in the negative direction, falling from left to right. And this is a negative weak correlation, negative 0.3. So, you know, anything here and here are high, right? Anything in this range are considered low. In this course, we will not compute the value of the correlation coefficient R, nor the equation of the best fit line by hand, but instead in lab you will actually use Microsoft Excel to compute the value of R. So if you look at this here, this is GPA and hours spent playing video games. So we expect a higher GPA for the hours spent playing video games to be low, right? Low hours spending video games is higher GPA. So we can have Excel find the best fit line, and it will output the value of R. So you can see that these data points aren't exactly on a straight line pattern, but they're pretty close, right? So this value of R is negative 0.84. It's negative because the line's falling from left to right. But it's a pretty strong, 0.84 is a pretty strong correlation. So using the regression line, so here we have age and size. The graph represents the age of an organism in millimeters based on its age in months. So it looks like these here are months, 2 months, 4 months, right? So this is months, it says age there, but that's months. And the size is in millimeters. So you are given the value of R squared. So a lot of times with this output, it will give you R squared. So R squared is 0.82. You are given the value of R squared. Find the value of R. So if we're given R squared and we want R, we do the opposite operation, which is to square root it. So you can get out a calculator and hit square root of 0.82. And the square root of 0.82 is 0.9055. So we know that anything close to 1 whole is a strong correlation. So if it is strong, because it's close to 1, it's close to 1 whole, is it reasonable to use the regression line to make predictions? Yes, because it's a strong correlation. So if this value, I think on the next slide we sort of have this kind of gauge about what R needs to be in order to use the regression line, but 0.9 is very close to 1, so we can use this line to make predictions. If the scatter plot looks like this, right, and Microsoft Excel fits a line to the data like this, the R is going to be very low. And so you shouldn't use the line to make predictions for this data set. You have to have a strong correlation in order to use the line. It also gives you the line here, although it may not look like your traditional y equals mx plus b form. It tells you that the size is equal to 0.83 plus 0.96. And then that asterisk up there, remember, means times the age. Okay, so it says use the given line, and so Excel would output something like this. All right, and I put down here, recall that y equals mx plus b is the equation of the line. So it's just y equals 0.96 times x. Age is like x. X is age and y is size, plus 0.83, just rearranging that. Okay, so 0.83, we want to use the given line to predict the size for after 5 months. So we would just plug in 5 there. All right, and so make sure you do the multiplication before the addition. 0.96 times 5 is 4.8 plus 0.83 should give you 5.63, and make sure that you put units on your answer. Those should be millimeters. All right, the age and then millimeters. What level of R is significant? All right, so you might say, well, is 0.7, is that large enough to use the line as a good predictor? The smaller the sample size, the more likely the correlation is due to chance. Thus, the level of R for the correlation to be significant depends on the sample size N. On the next slide, there is a portion of a chart showing a significance level of 5% and 1%. In statistics, those are the very typical significance levels. 5% means 0.05, right? We know that 5% means 5 divided by 100, right? Which is 0.05, and 1% is, of course, 0.01. And we use the Greek symbol alpha to indicate these significance levels. Alpha equals 0.01 and alpha equals 0.05. So if alpha equals 0.01, this means that when the statistician says there's a correlation, there is a 1% chance that there is not. Okay. On page 828 of the text, there's a much larger chart than the one that's in here. You can look at the online textbook if you want to look at the larger chart. But you can imagine that at the 1% level, there's a lot less chance of error than the 5% level, because at alpha equals 0.05, which is 5%, that means that there's a 5% chance of error, which is a much larger chance of error than 1%. So here's a portion of that chart. For N, remember N always stands for the sample size. And here we have a 5% chance of error or a 1% chance of error. So you can see, you know, with a sample size of 18, with a 5% chance of error, we have a correlation. This is a value of the correlation R. All these are R of 0.468, and at the 1% level, the correlation is 0.590. Right? You need a higher correlation for a 1% chance because there's less chance for error. Okay. Please note that R equals negative 0.6 is equally as strong as 0.6. Right? They're the same. It's just one is going this direction and one is going that direction, right? But they have the same strength, just like 1 is the highest and negative 1 is the highest, right? So the chart can be duplicated for negative correlation. So these are both positive or negative, right? Depending on, each one of these is positive or negative, depending on, you know, which direction the scatter plot goes. The correlation coefficient R is given for a sample of N data points. Use the alpha equals 0.01 column in the table to determine whether or not we may conclude that a correlation does exist in the population. So the first one is N equals 27 and R equals 0.4. So we're looking at the point, this time we're looking at the 0.01 level, right? And we're looking at N equals 27. So if N equals 27 at the 0.01 level, we can see that we have a correlation of 0.4. So what we need is R to be 0.497. That's what this chart tells us, right? In order for there to be a correlation with a sample size of 27 and an alpha of 0.01, we need the correlation to be 0.487, but we don't. The correlation for our data set is 0.40. So no, because 0.40 is less than what we need, which is 0.487. And part B says N equals 27, R equals negative 0.40, and this is also no, for the same reason. It doesn't matter if it's positive or negative, right? 0.40 is less than 0.487. It doesn't matter if it's positive or negative, right? It's the same strength, and it's not big enough. The correlation coefficient R is given for a sample of N data points. Use the alpha equals 0.05 column. This time we're going to use this one to determine whether or not we may conclude that a correlation exists in the population. Again, we're using N equals 27, and R equals 0.4 again. This is what we need in order for there to be a correlation in existing correlation. So we need it to be 0.381. So yes, our R is greater than the value in the chart, so we can assume that there is a correlation. Obviously, the higher the correlation, the more confident we feel about reporting data or reporting statistics. And this is the same thing. Yes, right, because 0.40 is greater than 0.381. Again, it doesn't matter if it's positive 0.4 or negative 0.4. So that's a given chart, right? Obviously, you can see that the larger as the sample size increases, right, the value of R needed in order for there to be a strong correlation decreases, right? Because we feel more confident for a larger sample size.